Hello, Math 109 students. We are looking at the QEP critical thinking assignment. I'm going to show you how to do it. I'm trying to think about the best way for you to submit this assignment. So when you submit this assignment, you should go to the Moodle course page and click on this icon right here, Math 109 QEP critical thinking assignment. If you click on this icon, actually downloads the document for you that you will either use on your computer and fill it out on your computer, or you'll print it out and fill it out by hand. But what you have to actually turn in, you click on this, and when you click on this, it'll allow you to turn it in. You should be able to turn it in that way. But the kind of file you have to turn in is either like a Word document or some sort of a word processing document or a PDF file. So if you have to print it out and fill it out by hand, you're going to have to find a way to scan it as a PDF file to submit it and turn it in. Most phones have the ability to download an app that will take a picture of a page and convert it to a PDF. I use one like that on my Android phone. It's called Cam Scanner, but there's probably, and it does it for me for free. There are probably others that do it on Android and others that do it on iPhones as well. If you don't have a scanner that can do it, or if you can't go to the library or to somewhere to find a way to scan it, save it as a PDF, and turn it in right here that way. Now let's look at how to actually do the thing. All right, obviously you want to put your name on it right here. Okay, we're talking about critical thinking here. That's what the QEP for GMC is about. It's about trying to improve students' ability to think critically. This is what you need in life. It's what you need. It's what companies want to hire. They want to hire people who can think their way through situations logically. So these are some skills that we are focused on: inference, deduction, induction, analysis, and evaluation. All right, you might want to look those terms up if you're interested in them. Just Google the definition of those things as it refers to the bigger topic of logic or critical thinking. This particular assignment only focuses on these two, evaluation and analysis, and here's what they are. Well, I'll go ahead and tell you a couple of things about these others. All right, so an inference is when you go from one piece of information and you draw an inference from that to apply to something more broad. All right. Deduction is when you take the laws of logic, and you deduce a conclusion from the higher up laws of logic. Something like, if all rectangles are quadrilaterals and all squares are rectangles, then all squares are quadrilaterals. So that would be an example of deduction. Induction would be when, like, evidence-based from the bottom up. So deduction is from the top down, induction is from the bottom up. So induction is like seeing, observing something, observing patterns in the world, and forming an inductive conclusion based on the pattern. So let's say something like, when I water this plant once a week, it grows this much. When I water it twice a week, it grows this much. When I water it 3 times a week, it grows this much, and so on and so forth. And then you can take the evidence that you collect and then form a conclusion about, well, what's the best watering pattern to use on this plant. So science is actually the induction. It uses the methods of induction, also known as empiricism or evidentialism. Deduction is philosophy, rationalism. All right. I know that's probably more than you want to know, but that kind of stuff really fascinates me. And I have a lot more to say about it, but I won't do it in this video. But we're focused on analysis and evaluation here. Let's talk about what those are. Evaluation. Evaluative reasoning skills enable individuals to assess the credibility of sources of information and the claims they make. And people can use these skills to determine the strengths and weaknesses of arguments. Evaluation skills can judge the quality of analysis, interpretations, explanations, inferences, options, opinions, beliefs, ideas, proposals, and decisions. Strong explanation skills can support high-quality evaluation by providing evidence, reasons, methods, criteria, or assumptions behind the made claims and reached conclusions. So evaluation takes the conclusions and the claims formed by these other skills and makes a judgment on those. So you can judge the strength or weakness of those claims and conclusions. Analysis. In that skill, you identify assumptions, reasons, and claims, and examine how they interact in the formation of arguments. Individuals use analytics to gather information from charts, graphs, and diagrams, spoken language, and documents. People with strong analytical skills attend to patterns and to details. They identify the elements of a situation and determine how those parts interact. Strong interpretation skills can support high-quality analysis by providing insights into the significance of what a person is saying or what something means. So interpreting information, gathering information from sources like charts, graphs, diagrams, languages, and documents. That's the skill of analysis. So keep these descriptions of these two skills in mind as we go through this assignment, because you're going to be asked at what point in the assignment were you doing the skill of evaluation, and at what point in the assignment were you doing the skill of analysis. How do you think the critical thinking skills of evaluation and analysis apply to the content we have discussed so far into the term? When you work through a mathematical exercise, do you use any kind of analytical skills? How do you evaluate your solution? Can you think of a time when you were using a mathematical formula to arrive at an answer? How do you know this formula is correct? Basically, when you are solving an equation and you're, let's say you just have x plus 2 equals 3, and so you want to find out what x is, and so you subtract 2 from both sides of the equation. When you're doing that, you're using the methods we're talking about here. You're using the deduction method, because you're using logic to say, if I want to get rid of a plus 2, then I'm going to have to subtract 2. That's because positive 2 and negative 2 cancel out and make 0 and gets x by itself. And I have to do the same thing to the other side of the equation. That's using deduction. So when you're solving equations, you're doing that. When you're looking at a graph and getting information from a graph, like you're looking at a line or a parabola or something, and you get any information from there, you're doing analysis. When you do something like, well, every parabola that has a positive leading coefficient opens up. So I think that I can conclude that if the leading coefficient is positive, then it opens up, and if it's negative, then it opens down. When you're doing that, you're doing induction, because you're noticing patterns. Whenever you go back and check your work, you're doing evaluation. Or when you plug your answer back into the original problem to see if it makes sense, you're doing evaluation. All right. Write down some thoughts you have about evaluation and analysis in mathematics, and we will discuss them together as a class. I went ahead and filled this out. All you have to do is write down exactly what I have right here. We use analysis constantly in math. Every time we read a word problem, look at a graph or chart, or draw meaning from these things, we're using analysis. We use evaluation when we arrive at a solution and then think about whether that solution makes sense in the mathematical world and in the real world context of the problem. So if you want to reword that in your own words, that's fine. Or if you just want to use exactly what I've said here, feel free to do that. Just put your answer in this box on that document. All right. Number 1, problem introduction. Consider the following. A medical researcher wants to determine the effect of pH. a measure of alkalinity or acidity, with pure water having a pH of 7 on the growth of bacteria culture. The data provided to you below represents the measurements of different cultures in thousands of bacteria after 8 hours. So I think, if I'm remembering correctly, and I'm not a chemistry major for sure, but I think the lower the pH, the more acidic it is, and the higher the pH, the more basic it is. If I'm wrong about that, I'm sorry, and maybe you know better than me, but I think that's the case. But you can see that we have these different pHs, and as the pH is changing, the number of bacteria are also changing. The number of bacteria that can grow inside of that pH changes as well. The number of bacteria is in thousands. Create a scatter plot to represent the data. Okay, so we have to create a scatter plot. So that means what we're doing is we're making these things be ordered pairs. So like my first ordered pair would be 4, 116. My second ordered pair would be 5, 120. I'm doing all these ordered pairs. So I'm going to try my best to do this, but it's kind of hard to draw on this computer screen this way. But my pH, that's so bad. My pH is going to be on the horizontal axis. And my bacteria cultures, my number of bacteria cultures, is on the vertical axis. And notice that this starts at 116,000. I'm just going to I'm going to assume that it's in thousands. I'm just going to put these numbers as they are. But if I'm going to start at 116 and go all the way to 163, then I'm going to definitely not start at 1. I'm going to skip some numbers. The way that you can show on a graph that you have skipped numbers is to put a kind of a squiggle like that. And that means that you've skipped over numbers to get to where you are on these. So if I'm going from 116 to 163, let me think about that. If I count by tens, then I'm just going to need 6. If I count by fives, I'm going to need about 12. I'm going to count by fives just to give myself a little more accuracy than counting by tens. So let's start this at 115. 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. And I might even need to go one more. 65. That's supposed to say 125 right there, 130, 135, 140, 145, 150, 155, 160, 165. And the pH just counts up to 11. So I'm just going to count by ones there. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, it definitely helps if you can make your dashes spaced out the same amount apart each time. I probably didn't do a good enough job with that, but you can see what I'm talking about. So 4, 116 is my first order pair. 4, 116 is about right here. All right, next 5, 120. 5, 120. About right in there. 6, 131. 6, 131. 7, 136. That's 4, 5, 6, 7. 7, 136. Probably not quite lining these up, I don't think. It's just hard to do on this computer screen. We'll do 5, 120 again. 6, 131. And it does. You don't have to. If you're not like super precise, that's not going to be a problem. It's not going to count off on you. Just do a decent job of this. 7, 136. 8, 141. 9,151. 10,148. Might be a little bit. 11,163. Okay, so something along those lines is what you'll need to draw on that, in that box. I need to label my y-axis. Bacteria in thousands. Right, based on the data and your scatter plot, what do you think a good linear function would be to represent the data? Justify your decision as best you can. So what we want to do here is just kind of try to eyeball this the best we can. Eyeball a line that goes through the middle of these points. The line can't go through all the points, but the line just needs to kind of split these points. So if I was trying to do that, splitting those points, I might do something like that. And that wouldn't be too bad of an estimate to split those points. All right. And so now we're trying to estimate a line, what the equation of that line might be. So let's do that. What do we need to estimate the equation of a line? We need y equals mx plus b, where m is the slope and b is the y-intercept. So we can get the slope. Remember slope? M equals y2 minus y1 over x2 minus x1. It's the rise over the run, right? Or the change in the y over the change in x. So we need to kind of estimate 2 points on our line. I think I see 3 points that kind of look like they are pretty much on our line. So you can, from at least for me, your line may not look exactly the same as mine, and that's totally fine. In fact, we all shouldn't get the same answer. You do yours not feeling the need to have the exact same line or the same exact numbers as me. We'll all be kind of close to each other, but it shouldn't really be the same between us all. But for my line, these 3 points, I could use any 2 of these 3 points. So I think I'll just use this one and maybe and this one, I guess. So what are those points? That is the point. I have to try to remember what that point was. That was the point 5, 120. And this was the point, let's see, 4, 5, 6, 7, 8, 141. So I'm going to get the slope based off of those 2 ordered pairs. So it's going to be, in my case, 141 minus 120 over 8 minus 5. And you can feel free to show your scratch, your calculations on this sheet as well. In fact, it's good to show that so that I know kind of how you arrived at your conclusion, and that I see that you're doing the work you need to do. So 141 minus 120, that's going to be 21. 8 minus 5 is 3. So that works out pretty nice, that my slope is 7. And it's obviously 7,000, but again, we're assuming everything is in thousands. So that means that every time I go up by 1 pH, I'm going up by 7 or 7,000 bacteria. All right, now I also need a y-intercept. So there's a lot of ways you can do this. You can do point slope form, but I think I'll just try to estimate my y-intercept like this. Okay, you can do it this way too. All right. So let's imagine our y-axis continuing to go down until it crosses right here. And so it doesn't matter, like this is 115, it doesn't matter that I'm getting below the x-axis. This is because I skipped so many numbers, this x-axis isn't actually starting on 0. And that's fine. So I'm just going to try to count down 110, 105, 100, 95. I think 95 would be a decent estimate. So 95 I think would be a decent estimate for me. It may be a little lower than that, maybe closer to 90, but I'm just getting an estimate. So B, I'm just going to let B be estimated as about 95. So that I now have an answer for this a good linear function. My good linear function would be something like I can say y equals 7x plus 95. Or I might say B of P. So like bacteria as a function of pH equals 7P plus 95 in thousands of bacteria. All right, so this is just kind of a way to write it as a line, but this is a better way to write it as a function where bacteria is a function of pH, so this is kind of preferred. Okay, how do we justify our decision? We justified our decision basically with our scratch work up here. All this scratch work is, and what I drew right here is the justification. Justification is up there. All right. With a partner, compare your solution. Evaluate your partner's solution. Is their justification logical? If we were in class, you would just exchange your work with somebody else, and you would just evaluate their work, and you would look at it and say something like, well, their line appears to be going through the dots, and they chose 2 dots on the line and found the slope, and their slope seems reasonable, and their y-intercept seems reasonable, and therefore their solution is reasonable and their justification is logical. Or you might even say, I think their line actually was too high. It didn't go through it didn't kind of split the points good enough, or it was too low, or something like that. Or I think they weren't neat enough on their y-axis, and so it looks like their y-intercept is actually higher or lower than what they said it was, or something like that. Or they made a mistake in their slope calculation, or you can think of all kinds of things you could say. But for now, I guess we'll just have to leave this blank because we don't have a partner to evaluate. Part 2 here of this assignment is about finding a least squares regression line, a linear regression, and that will find a line for this data that will be more than just, it'll be more precise than just an eyeball estimation of this line. This is a mathematical formula that minimizes the error, minimizes the distance between the points and the line. It finds the line that is the optimum line to minimize the sum of all these distances. All right, so this is a formula that does that. Now, we could plug all the x, y's in here, like all the pHs goes in for the x's, and all the bacteria go in for the y's, and we could find our a and our b to make the new m, the y equals mx plus b, to find the new mx plus b line that is a better line than the one that we estimated earlier. But I have good news for you, and that is we can use our calculator and it can do all that for us. All right, so it says, with the data provided, find the least squares regression line. So what we're going to do is we're going to plug all of these numbers into our calculator. All right, so we're going to go to Stat and go to Edit. And if you have anything in your lists already, we're going to clear that out. So to clear that L2, I go up to L2 and hit Clear and then hit Enter, and it clears the whole L2 list. Then I'm going to go over, click over to L1, click up there at L1 and hit Clear and hit Enter, and it clears the whole L1 list. So in L1, I'm putting in 4, 5, all the way to 11, which is all those pH values that are given in that table. Okay. And then in L2, I'm putting in all of those, all of these bacteria numbers. I'm going to pause it so you won't have to watch me. All right, so now that I've typed in everything for L1 and everything for L2, I click Stat again. I go to Calc, and I want to calculate a linreg AX plus B, linear regression. All right, so I'm still in the Stat menu, and instead of on the Edit tab, I'm on the Calc tab, and I go to option 4, which is linreg. So linear regression. I want the X list to be L1. I want the Y list to be L2. Let's say if you didn't have L1 right there, how could you get L1 to be there? Here's the L1, L2, L3, L4, L5, L6 right here above your buttons here. So if I want L1 to be right there, I hit second, and then that button there, and that'll put it there. So I want L1 there for the X list, L2 for the Y list. All right. I don't think we want a frequency list, so just clear that out. There shouldn't be anything there. And go to Calculate. And it calculates my linreg, my mx plus b, except it says ax plus b. So in this case, a is the m. So m, or a here, would be 6.36, and b would be 90.57. 6.36 and 90.57. So now I go to this square here, find the least squares regression line. It is, let's see, a equals 6.36 and B was 90.57. I think I remembered that right, but I'm going to click on my calculator just to make sure. Yes. So then Y equals 6.36x plus 90.57, or we could say B as a function of P equals 6.36p plus 90.57. All right. How does the least squares regression line compare to your original guess for a linear function to represent the data? Well, to compare it to what I had, 6.36, that means my slope was a little too steep, slightly too steep. So least squares regression line had a slope slightly less steep. And then what about the y-intercept? 90.57 versus 95. So, and a y-intercept and say a slightly smaller, or slightly less. You say slightly less or slightly smaller. Slightly lesser. I'm going to say slightly lesser. slightly lesser y-intercept. So if you say something like that, that'll be fine. Or if you put it in your own words that have much of the same meaning, that's fine. More regression. The medical researcher decides to take a few more measurements to have a more complete data set. The following table represents the finalized data set detailing bacteria growth after 8 hours. So what they added, all they added here was they had 4 through 11 already, but the researcher did one less than they had before. So he added the 3, 124. He added that ordered pair, and he did one more than what they had before, the 12, 155. So he added 2 more data points. With this new data, calculate a new least squares regression line. Your earlier work should help some. So all I really have to do here, since I'm doing this on my calculator, I go to edit. And the good thing is you don't have to put these in order for it to give you the right answer. You could put the 3 down here, 3 enter, but you do have to line the 3 up with the correct y value. So 3 for the pH and 124 was the bacteria value there. And then the other point was 12 for the pH, and it was paired with 155 for the bacteria. And I can just run my least squares regression again. So I hit Stat, I click over to the Calc tab, and I click option 4 for LinReg again, and I keep it set up the same way. XList L1, YList L2, nothing for the frequency list, nothing for the other thing, store, I don't even know what that is, nothing there, and click Calculate. And I have a little bit different A and B this time, a little bit different slope, M or A in this case, and y-intercept. 4.93 and 101.55. 4.93, 101.55. Isn't that what it was? Let me make sure I'm remembering that correctly. Yes. So again, y equals 4.93x plus 101.55, or B of P equals 4.93P plus 101.95. Alrighty. How does this new line compare to the old least squares regression line from part 2? So our slope went down a little bit. Slope went down. What we say? I'm gonna say decreased. Decreased slightly, and y-intercept, it went from 90 something, like around 90 to 100, so it went up, increased slightly. All right, write down the formula you calculated in part 3. Okay. So that means I'm just writing that down again, which seems kind of odd to do, but okay. B of P equals 4.93 P plus 101.55. Using this formula, identify the amount of bacteria cultures that would grow in a pH level of 7.5. Include your calculations. So all I have to do is plug 7.5 in for P. So B of 7.5 would equal 4.93 times 7.95, I'm sorry, 7.5 plus 101.55, and I'm just going to calculate that in my calculator. So I just typed this in my calculator and I got the answer 138.53. 138.53. Or we might round it to 139 bacteria cultures if we are just calculating it as a whole number. Also identify the amount of bacteria cultures that will grow in a pH level of 1. Include your calculations. So again, all I'm doing is plugging 1 in to that formula from before. That's going to give me 106.48, or we might say just 106 if we wanted to round that. Now, using your formula from part 2, find these same values. How do they compare? Which do you believe is more accurate and why? Okay, so my formula from part 2 was what? From part 2, got to remember it. 6.36p plus 90.57. So I'm plugging in 7.5. And I'm plugging in 1 to the equation that I got in part 2 instead of the one from part 3. And I'm going to calculate that in my calculator. Okay, I went ahead and calculated these in my calculator. And for the 7.5, I got 138.27. And that's almost right on the dot of what the other one got, 138.53. And for 1, I got 96.93, which is less than the 106.48 that I got with part 3. So I'm going to say, it says, how do they compare? So almost the same for 7.5. Part 2 came up with a lower result for 1, which is more accurate. I believe the equations from part 3 and the results based on, I should say the equation based on that equation is more, I should say are more accurate. Why? Why do we think they're more accurate, the part 1 from part 3? Why don't you think about that for a second before I say it? I think that the equation for part 3 is more accurate because it uses more data. So anytime you can use more data, you're generally going to get more accurate results. All right. Debriefing and conclusions, part 5. Write a brief response to some of the following thinking points. Do you think there is a positive, negative, or no correlation between the pH level and the growth of the bacteria? What calculation supports your response? What you think about that? I bet you already know the answer to that, but positive correlation. The slope is positive. That's a good enough answer. The calculation that supports the response is that the slope, we calculated the slope to be positive. And a positive slope means that it is a positive correlation. So let me just show you on this line. Positive correlation means that as the pH increases, the number of bacteria growing in the dish or whatever it is increases as well. That's a positive correlation. You can definitely see that there's a pattern there that looks positive. A negative correlation would be if it started out high and went lower as you go. No correlation would be if the dots were just kind of spread all over the place and did not seem to follow any pattern. But this is pretty good fit for a positive correlation. From your initial guess to your two separate calculations of least squares regression line, how did your model change? My initial guess wasn't too far off from the other two, but the model became more accurate when the data were used to mathematically calculate a least squares regression and then became even more accurate when more data was added to the model. Part 3. All right. Suppose that the researcher made a mistake in calculating the data and the pH level of 11. There were actually 263,000 bacteria cultures. What effect do you think this would have on the least squares regression line? Let me just show you what that would kind of do to that least squares. So what he's saying is, for 11, instead of being 163, if instead it was 263, that would be like way up here. You'd have this point way up here. And that would bring your line, for your line to then minimize the distance between all the points, your new line would have to it would kind of have to go up here now because that point's going to kind of pull that line upward. So if that point there was actually way up there, then our line would be very different. It would have it would be much steeper, and it may even affect the y-intercept, but it's harder to tell about the y-intercept, but definitely would make it steeper. So let's go down here. What effect did you think this would have on this squares regression line? That point would pull the end of the line upward, causing the line to have a significantly increased slope. All right. It isn't appropriate to model all data with linear functions. Sometimes quadratic functions, higher order polynomials, or even non-polynomial functions are used. Do you think that a linear function was an appropriate model here? Why or why not? So the question is, again, looking back at the data, do you think a line is appropriate for this data? In other words, should it be a curve? Would it be better to be a curve, or would it be better to be a line? It looks to me like a line is best. It looks more linear because the dots appear to follow a linear pattern. They're not curving downward or curving upward. Like curving upward, the points on the end would be going up, would be following a curvature pattern. But they're not. They're just kind of continuing on the linear pattern. That's what I'm going to say in that answer. A linear function was an appropriate model here because the data points seemed to follow a linear pattern rather than a curved pattern. Okay, write a brief response addressing each of these thinking points. How did you use the critical thinking skill of evaluation in this scenario? Did you use any evidence or justification to support any thoughts or calculations? All right, we used evaluation. When remember, evaluation is making a judgment on a claim or on a conclusion. Well, when we did our first linear model, when we just kind of eyeballed it, we then evaluated that, meaning we made a judgment on that when we did the model based on the mathematical calculations using the data. And then we made a further judgment on that one when we added more data to the model. We used evaluation when we improved our initial eyeball estimated line by using a data-based formula for the line, and then used evaluation again when we further improved our model by adding more data. All right. How did you use the critical thinking skill of analysis in this scenario? Did you analyze any charts or recognize any relationships amongst data? So analysis, remember, is interpreting what you're looking at and using it for calculations or something. So we used analysis when we interpreted the numbers in the table let's say we interpreted the meaning of the numbers in the table, and even when we read the words in each of the descriptions and tasks we were given in this assignment. All right, interpolation refers to estimating a value that is within known data. Extrapolation refers to predicting values that are outside of a known data set. When interpolating, we are using deductive reasoning, and when extrapolating, we are using inductive reasoning. What could the researcher do to evaluate your interpolations and extrapolations? So I would like to say here, we used interpolation when we calculated the number of bacteria for a pH of. So interpolation is when you plug in a value that is within the known data. So when we plugged in 7.5, that was interpolation because 7.5 was within the known data. The known data went from 3 to 12. 7.5 is within that. We used extrapolation. I know the question doesn't ask this, but I think I want you to write this anyway. We use extrapolation when we calculated the number of bacteria for a pH of what? Of 1. Because extrapolation is when it's outside of the known data set. So when we plugged in 1, that was outside of the range of data that we had. So now let's answer the actual question. What could the researcher do to evaluate your interpolations and extrapolations? The researcher could double check our calculations, our mathematical calculations, and or he could actually do the experiment with a pH of 7.5 or 1. And compare the experimental result to the mathematical calculation. Mathematically calculated result based on the model. Okay, is that the end? I believe that's the end. So you could read this, the last page here, meta-cognition, which means thinking about thinking. Evaluation is the process of judging whether an argument's conclusion is logical or not. Look at evidence that is presented and decide if it supports the conclusion. Use the right tool for the argument. If deductive logic is being used, evaluate if the premises are sound enough to lead to the conclusion. If the argument is inductive, evaluate if the conclusion is based on the premises. Evaluation. Evaluative reasoning skills enable individuals to assess the credibility of sources. I think we've already read the same thing up above. Analysis. A detailed examination of the structural form and content of some subject or situation, particularly as it relates to reasoning and interpretation. Strong analytical skills, we've already said all that. A mathematical model describes some phenomenon or system of phenomena utilizing mathematical concepts and language. These phenomena could exist in fields of chemistry, physics, finance, psychology, and so on. We use mathematics to describe the world around us. Based on the mathematics, we develop and draw conclusions about. Based on the mathematics we draw conclusions about the world. So you go from a real world problem to formulating a mathematical problem about that, related to that. Then you get a mathematical solution, and your interpretation leads to a real world solution from that mathematical solution, and you make sure that the real world problem and the real world solution match up based on the math and based on the real world context. And that is the end of this critical thinking assignment. Again, you need to get this turned in as some sort of a word processing document, like from Word or something like Word, or you could perhaps print it out and do this whole thing by hand with a pencil or pen neatly, and then you have to scan it somehow as a PDF with a scanner or perhaps with an app on your phone, and then you have to turn it in on the Moodle course page. If you will look at topic 7, you click on this icon and you'll be able to see where you can turn that in. So good luck on getting that completed, and I'll see you again in another video.